So today we're gonna do some practice problems for proofs and set theory. Exciting topic. I hope everyone's excited. Okay, the first one. Prove by induction that n factorial is greater than 2 to the n for n is greater than or equal to 4. So n factorial is just n times n minus 1 and multiply until 1. So for example, I think we should all know this, like 4 factorial would just be 4 times 3 times 2 times 1. Stuff like this. So that should be 24. Okay, what is the first step for induction?
Prove the base case?
Yes, but first of all, the problem statement is what? This should be simple.
N factorial is greater than 2 raised to the n.
Yes, exactly. So this would be our problem statement. And then what is the base case then? What's the base case?
N is equal to 4?
Yep, n is equal to 4. So we want to prove that P4 is true. That is the base case. So that shouldn't be too hard. Oh, I actually just accidentally did the example. But anyway, so n factorial. So in this case, 4 factorial is 4 times 3 times 2 times 1, which is 24. And then 2 to the 4 is 16. Right? So then that means 4 factorial is greater than 2 to the 4. So base case is true. So now what's the next step?
Our induction hypothesis.
Okay, inductive hypothesis, what is that? What do we assume to be true?
P of n plus 1.
We assume, so that's what we want to prove, right? What do we assume to be true for
P
our
of n
hypothesis?
is true.
Yes, P of n is true. So assume P of n is true. So this is what we assume. So P of n is basically the same problem statement, right? So n factorial is greater than 2 to the n for n is greater than or equal to 4. So now the inductive step, we want to prove n plus 1 is true. So we want to use P of n to prove P of n plus 1 is true. So let's write out what P of n plus 1 is. That should be too hard. We plug in n plus 1 as to the original problem statement. We get n plus 1 factorial is greater than 2 to the n plus 1. So this is what we want. This right here is what we want. I think it's really helpful to actually write out what you want. So, and then now we're just going to do some algebra. So then we will see how we can get to what we want. Any idea how to do that?
So if we write out the factorial n plus 1, we would have n plus 1 times n factorial.
Yep, that's exactly what we do. So n plus 1 factorial is n factorial times n plus 1. So we take out the last term. So then we know that n factorial is greater than 2 to the n. So this thing is greater than, we just basically substituted in, but then with instead of with an equal sign, we have a greater than times n plus 1. So now you see that this is actually looking already pretty similar to what we want here, right? But what do we need now? We need to have a 2 somewhere. So then we can get this 2 to the n plus 1 because 2 to the n plus 1 is 2 to the n times 2, right? So how do we get there? So since n is greater than or equal to 4, right? So this is stated in the problem statement. We know that n plus 1 is always greater than 2. It's always going to be true. So that means we can substitute it in again like this. And that gives us 2 to the n plus 1. And that is exactly what we want.
How are you able to make the assumption that n plus 1 is always going to be greater than 2? Do you just do it for, since n is always going to be greater than 4?
Yes, because n is always greater than or equal to 4, right? So no matter what n you plug in, n plus 1 is at least 5, right?
Right.
Yeah, so I mean, if n plus 1 is at least 5, if this is true, then n plus 1 is greater than 2 is always true.
Okay, thank you.
So I always find these proofs a little harder than the equality proof because you do have to think, like, this question that he just asked is like, n plus 1 is greater than or equal to 4. That is a more accurate, like a more precise statement. They're both correct statements, but this is a more precise statement. But what we want is actually the n plus 1 is greater than 2, not n plus 1 is greater than or equal to 5, in order to prove what we want. It's slightly weird, but I hope it makes sense. Any questions? Okay, we're gonna move on. So we have a pigeonhole principle problem. What is the fewest number of times you must roll a standard six-sided dice before you can be assured that at least 10 of the rolls resulted in the same number? So what do we do? Like, what is the pigeonhole principle? What is the pigeonhole principle? Like, what is the theorem? What does the theorem say? Somebody typed mn plus 1. Yes, but what is mn plus 1? Mn plus 1 is what? The number of times we have to roll. Yes, that is true. So, okay, this is a little trickier than the other pigeonhole problems that we've done before, but it's still not hard. So the theorem says that if mn plus 1 objects are distributed in, let's say objects are distributed in n boxes, we're guaranteed that at least one of the boxes would have at least m plus 1 objects. Right? So these are just like numbers, expressions, probably. So what we want to do is to fit all the numbers into these expressions if we can. So n boxes, we have a 6-sided dice, and that should be our 6 boxes. Is that obvious to everyone? I don't. So because there's 6 possibilities, right? You roll a dice, there's 6 possibilities. You can only have 6 numbers, 1 to 6, right? So then 1, 2, 3, 4, 5, 6. So we have n is equal to 6. So then each box has the number on them. So if we roll a dice, resulting in the number of 1, then we can put that roll into box 1. And we do that for every box. So what we want is at least 10 of the rolls resulting in the same number, right? So that means we want 10 rolls to end up in the same box. So what does that mean? That means m plus 1 is equal to 10. Does that make sense? We want 10 to end up in the same box, at least 10 to end up in the same box. So based on the theorem that we just reviewed, m plus 1 is equal to 10. So that means m is equal to 9. So now what do we do? How many rolls do we need? Any ideas? We have m and n already. How many rolls do we need? That means how many, basically that in this case is like how many objects that is.
6 times 9 plus 1.
Yep, 6 times 9 plus 1. That's exactly true. So we get 55. Yep. So this is kind of using the theorem, using the formula that we have. But if you want to think about it intuitively, we have 6 boxes, right? We have 6 boxes. And the worst case scenario is that we filled 9 because we want 10. We want 10 to end up in the same box, right? That's the goal. So let's say we fill 9 in each box now. So for the first 1, 2, 3, 4, 5, 6. So for the first 54 rows, we somehow got this. This is like the worst case possible. We get 9 in each box. So instead of like having 10 on the first try, we like somehow distributed it out and then we have 9 in each box. So then now the 55th try, like it has to end up in one of the 6 boxes, right? It has to end, it has to happen. So that's why intuitively, that's how we explain this 55 rows to get 10. Because, you know, it doesn't matter which one your 55th try actually end up in. We're going to have one of the boxes to have 10 rolls. Any questions? Nope. Okay. We're going to keep going. So this is set theory. We have set A, B, and C. And just to clarify, natural number in this case starts from 0. I know sometimes other people have different definitions, but in this case, that's not the natural number set. So we have A, B, and C, and then we want A intersect B or C. So first of all, can we list some elements from A? Can we list the set? What would A look like? A is equal to
4, 8,
go ahead.
12,
Sure.
4, 8, 12, 16.
What is the first? Yes, but what is the first one? What is the
It would
first?
be 4.
0.
Yes, 0. Yes,
Oh.
because natural number starts with 0, right? So then we have 0, 4, 8, 12, like you said, 16. Let's write one more. All right, so what about B? How do we do that, actually? So we have 2y is a perfect square, right? So first of all, what are the perfect squares? So z plus means positive integers, right? So we start from 1.
Uh, 1, 4, 9, 16, 25,
Keep going a little more.
36,
hmm
49,
Yep.
64.
Okay, and what's the next one? Keep going. Just keep
Oh,
going a little more.
81,
Uh-huh.
100,
And then
121, and
yeah.
144.
Okay, that's good. That's good. The problem that what I'm asking you to keep going because there are some of them that don't apply to set B, right? Because 2y is a perfect square, right? So all of these are 2y. These are 2y's. And then y has to be an integer. So that means 2y needs to be even. So in this list of number that we just listed, the odd ones don't apply, right? So these ones we can't use. So the rest we can use. So solve for y, we get 2, 8, 18, 32, 50, and 72. So that's our set B. It just keeps going. Right? So now what about C? We have to have z squared is less than 1,000. So what can z be?
Any number from 0 to 99?
But 99 squared would be greater than 1,000, no? It would actually be plenty larger than 1,000.
Would it be from negative 31 to 31?
Yes, that is true. So the set C, so you can actually check, like, 31 squared is what? 31 times 31. So 31 times 30 plus 1 times 31. So this is 961. Is that true? I think so. And then if you check 32 squared, it would be over. It would be something like 1,004 or something like that, I think. So let's set C, and then always remember when Z is in all the integers, it can be negative, right? So since it can be negative, it can be from negative 31, negative 30, 0, and on this side, we can go to 30 and 31. Make sense? Okay, so now we want set A intersect, so this right here, intersect with B or C. So what does that mean? That means that whatever element it is in the set has to be an A. It must be an A, but it can be in either B or C, right? So if you draw a Venn diagram to kind of see it, we have A, B, and C. So we have B union C is this part, right? And then A intersect with this. Do I have another color? A intersect with this part would just be this little chunk. right? So we want numbers that end up in there. So it must be in A, but it could be either in B or C. All right. Let me change it back to blue. Okay, so so I mean, in this type of problem, I would think that because the element has to be in A, so I have to pick elements from A that end up in B or C. So C is a pretty large set, right? C basically covers from -31 to +31. So we just have to find elements in A that actually end up in either B or C. So as long as they end up in one of them, it would be fine. So then we actually see that the entire set of A, basically whatever we've written down so far, this chunk at least, they all exist in C, right? So if that's the case, they all satisfy this A intersect B or C. So list 5 elements, you can just pick 5 from here, I guess 4, 8, 12, 16, and 20. As long as it doesn't go over 31, anything inside would be fine for set A. And there's nothing negative, so all the non-negative ones work. Any questions? Okay. So we have a Venn diagram problem. This should be fun. Use Venn diagram to verify the following properties of our set operation. One of the absorption properties, A intersect A union B is A. So all we want to do is to show that the left-hand side is equal to the right-hand side, right, with a Venn diagram. In this case, we only have A and B. So we can just draw 2 circles. We have A and we have B. So first of all, what is it? So A is this part, right? And then, so let's say like this is, we're doing left-hand side first. That's A. And then A union B is this, right? So A intersects that, so where is the overlap? So this is A union B. The overlap with C is exactly A. A intersect A union B. And the right-hand side, same thing. Is this. So we have left-hand side is equal to right-hand side. So done.
Quick question.
Go ahead.
For A union B, does it also include the overlap portion? Because
Yes.
I thought it was, okay. Because originally I thought it was, if it's an A, then it can't be a B, and then vice versa.
So this is like the or, right? This is like if it's in A or it's in B. So that means that it could be in either. That means if it's in the middle, that's in A. And so basically we're saying that this, how do I write this? So if we have an element here, X is in A or X is in B, this is what it is. So that means either if either of them is true, and if both of them are true, the statement is still true.
Okay.
Does that make sense?
Yeah.
Yeah, so there's also the exclusive OR, but I don't think we'll be talking about that. Exclusive OR actually excludes the overlap, but we shouldn't be talking about that, probably. It wouldn't be. Okay, we're gonna keep going. So another Venn diagram problem, use Venn diagrams to check whether or not you believe the following property is true. If it is not true, give a specific counterexample. What do we think? We basically do the same thing again, right? So we have left-hand side. I actually think drawing Venn diagrams is really helpful, at least for people who like to visualize things. Just easy. So we have A, B, and C. Let's label them A, B, and C. A minus B should be this part. So basically when X is in A, but it's not in B. So now, oh, these are really small. A, B, C again. So what is B minus C? When an element is in B, but not in C. Right here. I'm trying to color them so it's clear. Okay. So what is A minus B union B minus C? Put them together. We have this chunk from the A minus B. And we have this chunk from the B minus C. So that is what we get. Any questions so far with the left-hand side? Now I wish I was better at drawing really nice circles, but anyway. So we have right-hand side A minus C. We have A, B, C again. So A minus C, the element is in A, but is not in C. So it's right here. Right? Is that true? Is the statement true?
Yeah, it is true.
Yes, it is true. Really? I think the other way around is true, right? So this is not true. The other way around is true. So the A minus C is in this, right? Like where this sign right here is saying the left-hand side is inside of the right-hand side. Yes. The other way around is true. So if we want to say the right-hand side is inside of the, if the sign flips over, then that is true, but this is not true. And now we have to give a counterexample. Let me actually rewrite this. A minus B union B minus C is inside of A minus C, right? Yep. Okay. is a subset of. So what we can just give. So normally I would suggest just give like the simplest example you can think of. So let's say like A is equal to just one number, and B also, and C also. So what is A minus B? If A is 1, B is 2, C is 3. What is A minus B?
1.
Yep. Element that is in A but not in B, that is 1. So what is B minus C?
2.
Yep. Easy enough. So what is A minus B union B minus C? So the union of these two.
It's 1, 2.
Yep. 1, 2. All right. So then this is on the left side, right? So now we have on the right side A minus C. What is A minus C? If A is 1 and C is 3.
One.
Yep. It is 1. So that's a counterexample. 1, 2. So basically 1, 2 is not a subset of 1. So we just gave a counterexample. Any questions?
For making counterexamples, are we allowed to pick just any values for A, B, and C?
Yes, you can pick whatever. I just picked the easiest. So yeah. And the thing is like you do want to kind of guarantee, like you want it to be easy enough so you're not going to get confused when you're actually writing it out. So I think the easiest ones are great and they generally work out, but yes, any number would be fine. And any number of elements in a set would be fine too. Like if you really want something complicated, you want A to be a 1, 2, 3, and then B to be 4, 5, 6, like that's fine too. Okay, shall we move on to the next one? Oh, this one's about power set. Given the universal set 1, 2, 3, 4, 5, 6, 7, 8, 10, and sets A is 2, 4, B is 1, 2, 8, C is 1, 2, 5, 6, 10. Find the following: the power set of B intersects C. So what do we do first? We want to find the power set of some set. What do we do first?
So we find the B intersect C set first.
Yep. Okay. So what is a B intersect C? We have B is 1, 2, 8. C is 1, 2, 5, 6, 10.
1, 2.
Yep. Just look for the overlaps. Okay, so the subset, so power set means all the possible subset of the set. So what is the first one? The trivial one.
Empty set.
Yep. We have the empty set. And then we have what?
Set 1.
Yep, set 1. And then the next one,
2.
2. And the last one,
1, 2.
1, 2. Yep. Make sense? So I think you can, wait, actually you can write empty set as this. I don't know how, I think that would be fine too. But generally I would write the empty set.
So I have one question to clarify. So
Go ahead.
Is the empty set is in all the power sets? Is that right?
Yes, that is true. Empty set is in all the power set because that is always a subset of any set, right? Actually, wait. Yes, because even if it's the power set of the empty set, you still get the empty set inside. You just,
Right.
yeah.
I was confused between that with the like original set. I thought empty set was in the original set too. I was confused.
Oh, yeah, no. So empty set is just in the power set, right? So like empty set doesn't exist in B intersect C. Yeah.
Right.
It's
Thank you.
actually a set, even if it has nothing in it. Like it's not something that you can just put in any set. It's actually a set. It just
Right.
has nothing in it. Yes. Okay, any other questions? All right. Identify which of the following statement is true. For each false statement, provide a counterexample. You do not have to prove the true statement. The first one, for all sets A, B, and C, if A is in B, then the Cartesian product of A and C is a subset of B cross C. So just to clarify, I guess, like, I think we should probably know, like, A cross C, that's the Cartesian product of A and C, and then the elements look something like AC, where A is in A and C is in C. Cool. What do we think? Is A true or false? So if A is inside like this, if we have A is right here, this is B. So A is a subset of B. And what happens when you do cross like C? Looking like this.
Then you pick an element from A, put it with C.
Yes, I see. Yes, that is true. So if you want to prove it, it's going to be like, let A be an A, then we have, and right. So let A be in A and C be in C, then AC is in AC, right? And since A is a subset of B, as stated in the problem statement, A is also in B. So basically we're saying that if we have an element in here that's A, little a, it's going to be, if it's an A, then it has to be in the set B also. So that means AC is also in A cross B. No, not A cross B, in B cross C. And we're done. So we know that this is true. Make sense? Any questions? Okay, so what about B? For all sets A and B, A union B cross A minus B is equal to A squared minus B squared. What do we think? Any ideas? we can kind of draw a Venn diagram to see some intuition, I think. So if we have a B here, A union B would be this big thing, basically everything. And then cross A minus B. So this is A union B. A minus B would be this part, right? So the elements, so whatever tuple that we get, the first element is gonna end up in this whole, basically anywhere. And then the second element would end up in just A, not B. So then what about A squared? What does A squared look like? A squared is gonna be something like, oh, actually A1 and A2, where A1, A2 are both in A. So intuitively, the set A square minus B square. So if we have an element in the set A square minus B square, the element has to be in A square, right? The element has to at least look like this. And it's not in B square. It has to look like this. So that means this first element right here, this A1, has to be in A. Right? This A1 has to be in A. It cannot be in B. And that contradicts with what we just drew in a Venn diagram, because there could be some elements from the first element, this A1 could end up in B here. Does that make sense? Intuitively? That's how you kind of can figure out if it's true or false. So basically we're saying on the right-hand side, the first element of the tuple has to be in A. But on the left-hand side, the first element of the tuple can be in B sometimes.
That would make it false, right?
Right, exactly. Does that make sense? Hopefully that does. Any questions about this?
So when you take the Cartesian product of a set, you can just pick any point in it?
Yes, so it's not just pick any point, right? So like when you take the Cartesian product, it's actually all the points in it. So like you have to find all the possible pairs. That is the Cartesian product, is all the possible pairs that you can find that's in the form that the first element is in this, the second element is in this, all the possible pairs.
So it's kind of similar to a power set?
In a way, yes, but it's not all the possible subsets. I guess it's like all the possible sets with a restriction that the first element has to be in the first part, the second element has to be in the second part. Okay, so then we're just gonna give a counterexample. I wish we had more space. I should have done that, but anyway, what do we do? Okay, the next one is actually simple. So let's keep going with this one. So we want to give a counterexample, right? So we can actually do the same exact thing with B from the last one. We have, let me write the statement again. A union B cross A minus B is equal to A squared minus B squared. So that's the statement, right? So we do the same thing. Pick the simplest thing. I'm just gonna pick it because it's easier. C is 3. So A is 1, B is 2, C is 3. Okay, so A union B is what?
One, two.
Yep, 1, 2. And A minus B, we've done this before, it's 1. So what is A union B cross A minus B? What is this?
Would it be 1, 1, and then 2, 1?
Yep. So we're going to write 1, 1. So that's the first element. 2, 1 is the second element. So I do want to draw attention to the curly braces and the parentheses that we're using. So these are sets, right? And then in this case, 1, 1 is an element in the set. That's why we use the parentheses. So just be a little careful. So like, for example, if there is a set with just one tuple inside, so that means this set has one element inside, and that is a tuple. And that is not the same as writing something like this. Like this is a set of 2 elements with 1 and 2. Okay. But basically now here we have this. We have this, and this is our left-hand side. So what is a squared? So a squared is a cross a, right? And a is 1. So what is a squared? We have 1 cross 1. What is a squared?
1, 1.
Yep, 1, 1. So that is 1, 1 like this. What is b squared? B is 2.
2,
B is-
2.
Yep. B is a set 2. So we have an element looking like 2, 2. So a squared minus b squared is just a. Right? And this is definitely not the same as 1, 1, 2, 1. The set of 1, 1, and 2, 1. They're not equal. Cool. So we have the last one. Last one is actually this C right here. It's actually quite simple. You see that the formation is kind of different. Like basically, the first set would end up with something that looks like this. Like this is an element in the first set. So we have a tuple with the first element with a as an int and not an integer, as a number, and then the second element is a tuple. But then in the second set, an element in the second set would look somewhat like this, right? So we have the first element is a tuple, the second element is a number. So can they be the same if we have elements inside that look very different from each other?
No.
Right, so the statement is false, just based on that, intuitively. So we can give the same type of counterexample. So write the A cross B cross C is equal to A cross B cross C. So that's the statement. We still use the same thing. We use this A is 1, B is 2, C is 3. So what is A cross B cross, what does A cross B cross C look like? So on the left-hand side, we have 1 cross 2 cross 3. We have the order of operation. We have the thing that's inside of the parentheses would we would do that first. So what is 2 cross 3? What would that be? What would the set look like?
2, 3.
Yep, 2, 3, and element 2, 3 inside. So then A cross this would just be 1, 2, 3, like this. So this is one element inside of the set. Just that the first element of this one element is a number, and then the second element of this is a tuple. So we're going to do the same thing with the right hand side. Should be very simple. It's just we just change the order of operation. Oh, can't write. And that should give us 1, 2, 3. Something that looks like this. And they're not the same. So we're done. Not the same. So someone asked, is there something like A cross B cross C? Yes, yes, there definitely is. So A cross B cross C, this would just be like that. This would just look something like A, B, C. So all of the elements should look something like this. So that means this is one element inside of the set, not one element. So like all the element inside of the set should have 3 elements in each of them, and each of them are numbers or something, however you define A, B, and C. Any questions? Okay, we're done.